Let's talk about confidence intervals. You should be comfortable with probability, the z-table, and maybe most important of all, sampling distributions. So I'm going to talk to you about the logic of confidence intervals. I'm going to use the sampling distribution. That's what confidence intervals use, the sampling distribution, but let's be very tangible with this, okay? We know that sampling distributions are like other distributions, like a normal distribution. They are a normal distribution, but they're a distribution that is composed of the results of all the many samples. In this case, we're talking about sample proportions. So I have sample proportion number 170 here and sample proportion number 987 right there. All the many potential samples from a given population form the sampling distribution. And under the right circumstances, it's normal. You can refer to those videos if you need to brush up on that. And it's a distribution like any other. It has a mean, mu sub p hat. It has a standard deviation, also known as the standard error, sigma sub p hat. And so we can treat it like a distribution. That means that we can go a little bit further. It's a normal distribution. So I can specify, for example, that of all the samples that are possible in a given scenario, if I go from positive 1.96z to negative 1.96z, go ahead and refer to your standard normal table. If I do that, if I span a distance from positive to negative 1.96z, I'm going to be covering 95% of this sampling distribution. That means keeping in real, in the front of our minds that this distribution is composed of sample results, meaning samples, the results of actual physical potential samples. Then that means that we have 95% of all our actual, sounds funny to say, actual potential samples between these two numbers on the number line, whatever number negative 1.96z takes on and positive 1.96z takes on. That's actually 95% of the samples right there. So this leads us to the way that we can conceptualize confidence intervals. And I'm going to do that, and I'm going to list some steps in thinking going forward in this video right now that I want you to sort of pay attention to and think about. It's abstract, but we're going to make it as concrete as possible, and I want you to know that even though I'm going to do this in plain language, that it's going to be more rigorous than it sounds, because I'm actually going to be mimicking the very logic that's used in formal proofs that support the validity of confidence intervals, okay? So we're going to talk about it, and there's going to be some steps and logic that I want you to follow with me. Okay, so here's the first step in our thinking. There's a 95% chance that our sample is within this zone. Now, let's think about probability, and let's think about what we do and we don't know. We know that probability can be thought of as a proportion. It's a proportion of events rather than a proportion of a physical object. So we know that out of all the events called, let's take the proportion from this sample, or let's take the proportion, theoretically speaking, from that sample, 95% of the samples are between these two numbers. So that means that if we randomly select a sample, there's a 95% chance that the sample that we randomly select, or selected already in the process of our research, was one of these samples. There's 95% of the samples right there. So if you sort of shut your eyes a little bit and say, what's the probability that our sample was among those? It's 95%, because that's 95% of the sample. Okay? So there's a 95% chance that our sample, whatever it may have been, is one of them that's within that zone. And let me just mention, I keep using 95%. I'm going to use 95% as we start this video. There is no reason why you have to do a confidence interval with a 95% level of confidence. You can do it with any level of confidence you want, from 0 to 100%. 0 would be kind of silly, but you could do it and the math would work out. It would be a very silly thing to do, I suppose. 95% is sort of a default standard. Most confidence intervals are 95%. When a confidence interval doesn't list the level of confidence, automatically you can assume that it's 95%. And all the polling data that you see on TV or in the newspaper, assuming it's reported correctly and they give you an interval, they're usually not going to state the 95% confidence level. So if it's unstated, you can assume that that's what it was. So I'm going to stick to 95%, certainly to begin with, because I don't need to change a lot of things around while you're learning this. But we could be using any level of confidence. 90% is common too. Also 99%. And maybe we'll practice a little of that later. So out of all the samples, there's a 95% chance that ours was among those. Here's the next step in our thinking. If there's a 95% chance that whatever sample we took was among those, then we can equally say that there's a 95% chance that our sample is within the distance of 1.96 sigma sub p hats, meaning standard error is the standard deviation of this thing. There's a 95% chance that our sample is within the distance of 1.96 standard errors of p, the population proportion. That's the mean of this distribution. So we're actually now able to convert that into a distance statement. There's a 95% chance that our sample, whatever it was, is within this distance, whatever 1.96 standard errors is, of the absolute truth. So we're already able to make a distance statement from the absolute truth with a confidence level. We'll go further. Okay, so this is where we really sort of logically turn the corner and make what we've been building up to really useful. So notice what I did. By the way, this is the third step. In the last segment, I left it Roman numeral 1. Go back, squint a little, and pretend you're seeing a Roman numeral 2. This is kind of a backyard operation. Pretty low budget, so I'm not going to reshoot that part. I'm going to have you use your imagination. Anyway, this is the third step in our logic. So third step, and most important one. If in step 2, we can say that there's a 95% chance that our sample is within 1.96 standard errors of the true population mean, the truth, then that also means that we can turn it around. That's the beauty of distances. That's why we talk about them with absolute value, because they work both ways. If that spot over there is 5 miles from us, then we are 5 miles from that spot. That's true, right? So the statement that I made in part 2, I can turn around and say the other way. If there's a 95% chance that our sample is within 1.96 standard errors of the true population proportion, then I can also say this. There's a 95% chance that the true population proportion is within 1.96 standard errors of whatever our sample was. So you see, we've done something really important just by utilizing logic and realizing the absolute value signless nature of distances. We've made our sample result a sort of an anchor, a concrete foundation. We say whatever the heck our sample result was, there's a 95% chance that the truth is within 1.96 standard errors of whatever it is that we got. Now, it's true. Our sample might have been completely wacky, total whack job by accident, totally way off, but that's in the other 5%. Utilizing these figures, 1.96 standard errors going up and down, using the 1.96 figure, we can actually state that the true population proportion is within 1.96 standard errors of whatever it is that we got for our single lowly, humble sample. We say that we have a radius around our point, this is the way it's spoken of in math, of 1.96 standard errors, and the true population proportion is within that radius. Okay? Now that's the concept. I want you to think about the concept and get the idea, because I think it's really important. But in the next part of this video, we're going to cementify this and condense it into, okay, what's the procedure? How do we move forward? I just want to do one. So we're going to do one or two. So let's talk formulas. Okay, so here's a formula, a theoretically based formula for a 95% confidence interval. It's not entirely useful, and I'll show you why in a second, but it'll provide us the basis. So 95% confidence interval. That would be your sample result, your sample proportion, plus and minus 1.96, that's where the 95% comes in, times the standard error. The standard error is p times 1 minus p over n, and then the square root is taken. So that's the basic formula. What's wrong with this? Well, for one thing, we don't know what population p is, so how the heck are you going to be able to calculate this formula, which is supposed to be a confidence interval for population p, without knowing what it is? So here's what we do in reality. Here's generally what's really done. For a 95% confidence interval, we're going to use p hat itself as part of the standard error calculation. And that is okay. Especially the larger the sample you get, the less of an error that really introduces. And this is the way it's done. So that's the formula we're going to use. P hat plus or minus 1.96 times the standard error. Here's another common way to express it. We have p hat plus or minus, I like to actually use this myself, z star times, and I'm just going to write sigma sub p hat here, indicating the standard error. I like to write z star when I'm talking to my students or anybody else, because I like to remind folks that you don't need to be stuck to 95% confidence. You can use the z value appropriate for any level of confidence you want. For example, common values. 90% confidence would require, let me write an arrow, 1.645 z. 99% confidence would be, if you look it up on most tables, it'll be 2.57 or 2.58. Those two numbers are usually bracketing just about symmetrically 99%. So I like to use 2.575, which is the mean of those two numbers. And there's other numbers that will tend to recur over and over again. 98%, I'm not going to write that down, would be 2.33z. So there's various numbers that tend to recur over and over again. I said earlier that 1.96 is the biggie that's used much more than anything else. But there's nothing that stops you from getting a confidence level of any wacky number you want. 93% confidence, you could look it up on the z table and find the z value that would give that to you, and you can come up with it, and it's not even that difficult once you get practiced at this. Let's do an example. Okay, so let's go back to our previous example. We were looking for the amount of support for candidate A, because they're a really good candidate. So it turns out that our sample showed 60% support for candidate A. Now, I think while I was talking about it, I said, well, let's propose a sample size of 100. But as it happens, I went back and I calculated what sample size we need in order to make the math that we're about to do work the way I want it to, and it turns out we need about 368.796. Now, I'm not going to cover it in this video, but you can do sample size calculations where you calculate the level of the sample size, the size of the sample that you need in order to achieve some certain level of precision in your sampling distribution. We're going to talk about that, in your confidence interval. We're going to talk about precision versus your sample size pretty soon in this video. But I did the calculation. It turns out we need about 368.7936 people in our sample. Well, of course, There's no way you can have 0.7936 of a person, and you'll see soon that if I go smaller, I lose precision. So with sample size calculations, no matter what the decimal points are when you're talking about people, you always round up. So if this had been 368.01, I would still have to round to 369, and that's what we're going to do. So we're going to say that our sample size is 369. Remember, for the standard error calculation, since we don't know the population p, you're going to utilize the sample p. If you go ahead and calculate the standard error, and if you want to do it on your own, pause the video right now, because I'm going to go ahead and write what I got, utilizing a sample size of 369. I got standard error equals 0.02551. So that's our standard error with a sample size of 369. Remember what our formula is. Our formula is, and we want 95% confidence right now, because that's what I'm sticking with for right now, because it's the easiest one and most common. We want 95% confidence, so I'm going to take my p hat, my sample result, my sample proportion, and both add and subtract 1.96 standard errors, because that's actually what we're working with in this video. 1.96 standard errors. And let's go ahead and fill that in. And if we calculate that, we're going to get two numbers. We're going to get the number where we're adding and the number that results from subtracting. So let's go ahead and do that. Try it on your own and see what you get. Okay. What you should have gotten is what we were talking about before. That's why I recalculated the sample size, because this gives me what I was talking about a little bit earlier, the 0.55 to 0.65. This is what you ought to have been getting as you did this. So we say, I'm going to use a percentage this time rather than a decimal. We say that the probability is 95% that the true population proportion would be between 0.55 and 0.65. That's the true population proportion. Something that you should notice. Whatever your confidence interval is, your sample result is always in the middle. It's always symmetrical around your sample result, right? So that's why it has to be a wide window, because our sample result might not be centered right on the population proportion. It might be a little this way or a little bit that way. So we need to cast a wide net in order to make sure that we're capturing the population proportion. Here's the next point I want to make, right? I just made the point that your sample result is always in the middle of your confidence interval. Let's make another point. If anything, this is more important. Look, let's say we increase our sample size. Our sample size just now was 369. Okay, what happens if we really bump up the sample size and make it, say, 10,000? I chose that because it's a big number and it's a perfect square. It makes things very easy. I still want 95% confidence. I still want to report back to my bosses at the polling firm or whoever they may be that I can still make my statement with 95% confidence, which is pretty good. But I want to be able to make it with a much bigger sample. I'm asking the question, what happens to our precision? Okay, so go ahead and calculate that on your own. When I come back, I'll put down the answer too. Okay, well, here's what happened for me, and I think probably for you too. We utilized the new sample size of 10,000, and I calculated a new standard error, a sigma sub p hat, and I got 0.004899, okay? You may see the point that I'm trying to make already, but let's go through and plug in our values. We're going to take p hat and add and subtract 1.96. Keep in mind, I'm sticking to this 1.96 number. So that means that I can continue to say whatever I'm going to say with 95% confidence. My confidence has not weakened at all. 1.96 times what that standard error was. I'm running out of room, but I got it right there anyway, so we're okay. And I got these two numbers. I got 59, I rounded, 0.04% and 60.96%. Let's contrast that with what we had before. Earlier, when I had an N of 369, my confidence interval went from 55% to 65%. So here's what I'm getting at. Here's my point. When you increase your sample size from, in this case, from 369 to 10,000, when you engage in any increase in your sample size, if you don't change anything else, your confidence level stays the same, but the confidence interval narrows. In this case, it narrowed quite a bit, okay? We have a confidence interval that spans, not even 2%, goes from 59 to just under 61, 59.04 to 60.96. That is very precise. That's very precise. If you sit back a little bit and think about it, that's kind of a pretty neat and, to me, fascinating thing that you can get from one simple sample, pretty large in this case, yes, but from one sample, you can make a statement about the whole of the population, reality, with such precision, 95% confidence that the true population proportion would be now between these two numbers. By the way, increasing your sample size, and remember, unspoken until now is the assumption that we're sampling truly randomly, that we're engaging in responsible and correct sampling that's random. Otherwise, the results are not useful. But assuming we're engaging in correct random sampling and we're not engaging in any systematic errors, because they can be murder for the accuracy of your confidence intervals. Assuming we're doing that, then you can gain this advantage and utilize it in different ways. What happens if we say to ourselves, well, we don't need that much precision. That's actually more precision that we need. Let's specify a different number here for our Z star, 2.575. I'm going to leave that for you to calculate. And if you're not sure about your answer, post it to me in the comments below, and I'll tell you yes or no whether that's correct or not. We could bump up this number right here. That would give us 99% confidence, and we'd still have a fairly narrow, more narrow than this, a fairly narrow confidence interval. So an increase in your sample size when done correctly, randomly and so on, you can gain advantages in both precision and confidence. Let's go ahead and I'll pose a couple of problems to you that I will answer at the beginning of the next video, which is going to be about confidence intervals for population mean. Let me go ahead and pose those questions though. Okay, so here are some good problems that should start us off pretty well. I'm going to answer these at the beginning of the very next video. Let's start with this. And by the way, whenever you're doing these confidence intervals, generally as a budding statistician, you want to check to make sure that you have normality. You may need to go back and refer to sampling distributions to see what the rules are to ensure normality in a sampling distribution. In this case, you're probably going to want to do that with every one of these examples, because if you find that the sampling distribution is not normal, you cannot proceed with the confidence interval, and you'd simply write, not possible, not normal distribution or something, if it were a test paper or something like that. If you're an actual researcher or statistician, you would go to other methods. You wouldn't be able to use the method that we're using here. But those methods are not as good, and this is the true way that, as far as I know anyway, actual political and marketing polling is generally done. My point, check all of these for normality. Here's our first example. You're researching something, and your p hat, sub 1, is 0.78. 78% of your sample agrees with you or decides to buy the product or whatever it may be. Your sample size is 40. If you can, I want you to give me a 90% confidence interval. Second one, p hat sub 2. P hat is 0.48. Your sample size is 200. Let's do a 90% confidence interval with that also. P hat sub 3 is 0.71, sample size of 400. Let's do 95% with that. And then finally, your fourth p hat sub 4 will be 0.04. You're using a sample size of 250. And let's go for that brass ring. Give me a 99% confidence interval for that. And at the beginning of the next video, I'll show you the answers to those. Thanks a lot.